Let us now start with understanding the basic working of an induction motor. Okay. So there will be a stator and this will have windings which carry three-phase balanced currents, right? And they are 120 degrees spaced from each other spatially, right? And this will give rise to a rotating magnetic field which is in the clockwise direction, or if you change the configuration of the windings you can get in the counterclockwise sense as well. This is the stator part of it. Stator is something which is stationary, it won't move. Next we will take a rotor. Now just like the stator has windings which carry three-phase currents, in the rotor also we will have some windings. So first we will take one coil. Now this is a stationary coil. Initially the rotor is not moving and the coil is not carrying any kind of current. What is the only thing that is happening? The stator windings are carrying three-phase currents which is resulting in the production of a rotating magnetic field. Okay. So now when you take a single conductor, what happens when you take a conductor? Let us say you have a magnetic field which is in this direction, and this conductor, it is moving with a velocity v. Then what will be the induced voltage? The induced voltage will be v cross b, the velocity vector and the magnetic field vector cross product dot L bar. The induced voltage can be found from this expression. Now in this case what we have taken that the magnetic field is stationary and this conductor is moving with velocity v. And here what is happening? We have a conductor which is stationary, it is not moving, but the magnetic field is rotating. That means there is what you call as relative velocity between conductor and magnetic field. So first we will take the magnetic field vector. This is the magnetic field vector. We will take it as Bs bar, the magnetic field of the stator. We are going to have a rotor field as well, so that's why we are using the subscript S. Now this vector is rotating in the clockwise direction. Now if you consider in the other way, that means the magnetic field is constant but the conductor is moving. Okay. And it will be easier to apply this induced voltage expression. Okay. So now if the magnetic field is rotating in this direction, with respect to magnetic field, the conductor is moving in the opposite direction, right? So that means if you consider the magnetic field as stationary and you find out the relative velocity, then this conductor will effectively be moving in the opposite direction, that is in the counterclockwise direction. This is the direction of velocity. So now we have established the vector, velocity vector and the magnetic field vector. So now we can find out the induced voltage direction, which polarity will be produced in this conductor. So we will redraw this vectors separately. This is velocity and this is the magnetic field, the stator magnetic field. So Bs bar. Okay. So now if you do V cross B, if you apply the right hand rule, then which direction will your thumb be? It will be in the downward direction. So that means the positive polarity will be at the other end. So that means if you are taking the conductor top view, this is okay. Now the same conductor, if you are considering the front view, okay. Now since V cross B we got in this direction, this will be the positive polarity, this will be the negative polarity. Then in what direction will current flow? It will flow in this direction, right? So that means here in this conductor the current direction will be into the plane. So you can write like this. Now this, what about this conductor? The velocity vector is here for a stationary magnetic field, then opposite side. That means the current will be coming out of the plane. So this is how, by sending three-phase balanced currents onto the stator winding, right? So you can write this down. This is stator and this is the rotor. By sending three-phase currents into the stator winding, we get a rotating magnetic field which will induce currents in the rotor windings. It is able to induce currents because there is a relative velocity between the conductor and the magnetic field. So first you can write down this point here. First, what is happening? Three-phase currents flow in stator winding. And because three-phase currents flow, what is going to happen? A rotating magnetic field is produced. So this might feel like repetition, but only when you can consolidate in this manner you will be able to remember in the long term. Okay. So once RMF is produced, this RMF is going to result in a relative velocity between rotor conductor and RMF. And because of this relative velocity, what is happening further? Rotor currents are induced. Okay, so this much we have seen. All of this you can consider as part A, the induction of rotor currents. So you can write here part A. Now next what we want is, we want to find out how the torque is induced. Okay, what is the mechanism of torque production and also what is the direction. So that we will take as part B. Let us redraw the setup here. Now we will take each of the conductor here and we will see what is the force that will be induced. See, when will force be induced? The expression of force is IL cross B. Whenever there is a current carrying conductor in a magnetic field, then it will experience a force, right? So here this conductor, if you take, it is carrying a current in the downward direction, that is into the plane, and there is a magnetic field like this. Okay, so current is there, magnetic field is there. So it will experience a force. Now what is the direction of the force? So IL bar will be into the plane, B will be like this. So if you apply the cross product, then you will get the force direction, the cross product direction in this direction. Now what about this conductor? Here one vector is in the opposite direction. The length current is going out of the plane, right? So the force will be in the opposite direction. Now this is the rotor. One conductor on one end of the rotor, you have force on this side. On the other conductor, force on the opposite side. What will be produced? Torque is produced. And what is the direction of torque? In the clockwise sense. So here the relative velocity between the conductor and the magnetic field is in the counterclockwise sense, but the torque that it is actually, the rotor that it is facing, is in the clockwise sense. So do not get confused. Just because it is V, do not think that torque is in the counterclockwise sense. Okay. In fact, since we are talking about part B, wherein we are talking about the direction of torque, we don't want how the rotor current is induced. Okay. Relative velocity comes into picture when we have to understand the rotor currents. To understand the torque, we don't need the relative velocity. What we need is the current direction and the magnetic field. So this is part B. You can write here, after rotor currents are induced, we go into part B. What is part B? Rotor conductor experiences force. Why is that? Because it carries current in presence of magnetic field, stator magnetic field. Okay, and this force, since it is applicable on one side of the rotor, it is in one direction, on the other side it is in the other direction, so a torque is produced. Okay, so this is part B. So now we can see the entire working in these 6 steps. What are we giving? 3-phase currents we are giving, and all of this process is happening, resulting in a torque. This is how the induction motor works, the basic working principle of the induction motor. Okay. Next thing you need to know in understanding the working of induction motor is the speed, right? So the rotating magnetic field, what was the speed of the rotating magnetic field? It was given by 120 Fe by P, where Fe is electrical frequency in hertz, right? This is the electrical frequency of the stator currents. And what is P? Is number of poles. Do these poles actually exist? No. They are just representation of the rotating magnetic field. Okay. how many number of poles are produced for the given configuration of the stator conductors. Now this speed is what we call as the synchronous speed ns. Okay, ns is the synchronous speed. This is the speed with which RMF is rotating. Now what about speed of rotor in the induction machine? This speed, if you take as n, then this will always be less than the synchronous speed. Only then the motor will run. So why is that? We know that the induction motor is working in the first place because there is a relative velocity between what? Between the rotating magnetic field and conductors. Now what will happen if the speed reaches the synchronous speed? If you see the diagram once again, the rotating magnetic field is in the clockwise sense, and what is the direction of torque that we got? Torque also we got in the direction of clockwise sense, same direction as RMF. Okay. So now if the rotor speed reaches the speed of RMF, okay, then what will happen? Both are in the same direction. What will be the relative velocity? If the speed is n, then the relative velocity between RMF and conductor will be equal to the synchronous speed minus n, because synchronous speed will be greater. That is the cause. So it will be greater. So when both are moving with different velocities in the same direction, then the relative velocity will be the difference between the two, ns minus n. Now what will happen when n reaches ns? It will simply become, this ns minus n will simply become 0. And once this becomes 0, then there will be no force. Okay, and when there is no force, there is no torque, there is no working of the induction motor. This relative velocity we call as the slip speed. Another common term that we use is the slip. This is represented as S. This is nothing but the slip speed in percentage. So that means ns minus n, the slip speed as a percentage of the synchronous speed, okay, into 100. So this is what is the slip. You can either represent in terms of percentage, or just this term will also, we call it as slip. So we can write these two as a sort of summary. The slip speed or the relative velocity between RMF and conductor. This is given by ns minus n, where ns is equal to 120 Fe by P. This is called as synchronous speed, and n is the speed of rotor, the mechanical speed of the rotor. And next is the slip. This is represented as S. This is given by ns minus n, slip speed as a percentage of the synchronous speed. Now once we know the slip and the synchronous speed, we can represent the speed of the rotor in terms of the slip. So what will you get? N is equal to 1 minus S into ns. Now this n is in revolution per minute, right? 120 Fe by P when we are taking, we get in revolution per minute. Even the angular velocity, this can also be expressed as 1 minus S into omega S. So we have talked about the stator magnetic field and the rotation of the torque induced on the rotor. Now these rotor conductors, current is passing through them, right? And these rotor conductors also, they will be in a similar configuration. So when you take a rotor, here also you are going to get 3-phase windings, okay, so that are spaced 120 degrees apart. So then this will also produce a rotating magnetic field of its own, right? So current in rotor conductors produces an RMF of its own. Okay. Now what is the, how do we represent it? We will represent it as BR bar. Now what will be the phase difference between the stator magnetic field and rotor magnetic field? That means at one particular instant of time, if the stator magnetic field is here, then where will the rotor magnetic field be? It will be a little lagging. Why is that? Why is there a lag? See, the rotor currents that are being produced, this will be lagging the induced voltage. Okay, so you can write this point down. Rotor currents lag induced voltage. Why is that? Because of the inductive nature of the winding. Right, windings will be inductive. So that is why rotor currents will lag the induced voltage. So that is why the magnetic field that is produced by the rotor, that will also lag the stator magnetic field. So BR bar lags BS bar. So this we are considering as lagging because the fields, both fields are moving in the clockwise sense. Okay. So do not get confused. When we talk about the vectors, usually we talk of BR as the leading vector. But since the rotation we are taking in the clockwise sense now, the magnetic field is rotating in the clockwise sense. So BS is going ahead of BR. That's why we are taking lag here. Okay, so don't get confused. You can write down here because rotation is in clockwise sense. Now what about the electrical frequency of rotor current? Okay, electrical frequency of current in rotor conductors. Will it be same as the frequency of the currents flowing through the stator, or will it be different? So we have taken Fe as the electrical frequency of stator currents. Right? E represents electrical frequency to differentiate from the mechanical frequency. So now how do we represent electrical frequency of rotor conductors? We will take this as Fr. Okay. So this Fr is found out to be, it is experimentally found out to be equal to slip times the electrical frequency of stator currents. Okay. So if the motor is, let us say, it is running at synchronous speed, then what will happen to the slip? Slip will simply become 0 because S is the difference between the synchronous and the actual speed. So when actual speed becomes synchronous speed, S will become 0, then frequency will become 0. That we already know. Why? When there is no relative velocity, then there will be no currents produced. So the frequency will also be 0. Similarly, if the rotor speed we are making it 0, that means we are blocking it so that it doesn't rotate, then what will happen to slip? Slip will become 1. S is equal to 0 for the speed equal to synchronous speed, and it will be equal to 1 for n is equal to 0. Okay, since it is equal to the difference between the actual speed and the synchronous speed. So when S is equal to 1, what will happen? The frequency will simply be equal to the electrical frequency of the stator currents. Why is it like that? Because when the motor is not rotating, then it will simply function as a transformer. So let's say if this is the stator, you are energizing the stator, then the rotor will also have an induced voltage resulting in induced currents. This is for locked rotor condition. It will simply act like a transformer. So that is how Fr, the rotor frequency, it will be dependent on the slip. Okay. And finally, one more point is about the speed of rotation. See, what are all the rotating things that we have? We have the stator RMF. This is anyways the speed of this we are calling as the synchronous speed. And what is the speed of rotor? This we are taking as n. Okay. Now what is the speed of the rotor RMF? This is speed of stator RMF. What is the speed of rotor rotating magnetic field? Just like Ns is equal to 120 into Fe by P, where Fe is frequency of stator currents. the current that is producing this RMF, that frequency will be here in this formula, right? So the speed of rotor RMF also you can write something similar. N rotor is equal to 120 Fr by P, where Fr is frequency of rotor currents. That means the frequency of currents which is producing this RMF. But there is a catch here. This speed is with respect to what? Is it the actual speed or is it with respect to the rotor? Okay, because rotor itself is moving with some speed, right? It is moving with the speed n. So what will be this speed? Will it be with respect to the rotor or the actual speed? That means with respect to a stationary object. Okay, it will be with respect to the rotor. Why is that? This formula that we have got, we have obtained it. See, Ns is equal to 120 Fe by P. We got it with respect to the stator poles, right? So similarly, even the rotor RMF, when you use the same formula, it will be with respect to the rotor poles. So this speed is with respect to the stator. Here this is with respect to stator, but since stator is stationary, there is no problem here. But since this is with respect to rotor, which is a moving frame of reference, we also want to find out its actual speed. That means you can say with respect to the stator, which is stationary, what will be the speed. Therefore, actual speed of rotor RMF, what will it be? You can take the rotor here. This is the rotor. This is moving with a velocity n. And now we want to find out what is the velocity of this rotor RMF. Okay. So we know the relative speed. The relative speed is 120 Fr by P. The actual speed will be the relative velocity plus the speed of the rotor. Why we are taking plus? Because they are moving in the same direction. So to get the actual speed, we need to add the relative velocity. So this is going to be 120 Fr by P plus n. Okay. So what will you get here? 120 into Fr you can write as S into Fe by P plus n you can write. Now this term will become S times Ns, because 120 Fe by P is synchronous speed, Ns. So Sns plus n. Now n also you can represent in terms of synchronous speed. How? Sns plus n you can write as 1 minus s into ns. So you are going to get ns. That means the actual speed of the rotor RMF is the same as the speed of the stator RMF. The synchronous speed is equal to the synchronous speed only. But with respect to the rotor, the speed of rotor RMF is 120 Fr by P, which you got as S times the synchronous speed. Okay. So you can summarize here once again. Speed of stator RMF is equal to synchronous speed. Speed of rotor we are taking as n, which is nothing but 1 minus s into ns in terms of slip and synchronous speed. And finally, speed of rotor RMF you can mention here with respect to stator. Stator means any stationary object. This is equal to synchronous speed. And finally, speed of rotor RMF with respect to rotor. This is equal to S times ns. Okay. So these are the points that you need to remember.